since I was about 10 years old. My parents bought me a little cardboard and plastic telescope, similar to the one that Brandon had when he was a kid, right from Sears. And it was a great little telescope. I used it until it died. And then met my wife, Barbara. Hi. Thank you, Barbara, for being here. Barbara drove me here today, so thank you very much for that. Yes, all the way from Greensboro. Isn't that sweet of her? But I met her in astronomy class and in Appalachian State University. And then I got hired by the Greensboro Public Schools in North Carolina. And I taught astronomy and humanities and a bunch of other stuff there. And I retired in 2000, Barbara, was it 2005? 2004. And in 2008 was hired by High Point University to teach astronomy at High Point University in High Point, North Carolina. And I've been there ever since. So it's really a fun subject. I just love talking about astronomy. And that's how Brandon and I met, is talking about astronomy on Periscope, on the internet. And I just love talking with people. And I learn a lot from the people that I have conversations with, because I'm a pretty good listener. I'm okay at talking, but I'm a pretty good listener. So if you have any questions, any comments, please feel free to interrupt any time. That's all right. And I'll stop and listen. And I've been teaching for more than 30 years, so I'm really good at saying, I don't know, because there's a lot of stuff I just don't know. So I'm okay with that, and I'll let you know when I don't know. So I'm going to speak this evening about how far away are the stars, and more importantly, how do we know? How do we know how far away the stars are? And I use a model here. Astronomers use something called the cosmic distance ladder. And so I use a real ladder as the illustration. And this is just a model. All models, as I've been told, and I say in my classroom, all models are wrong. All models are wrong, but some are useful. And I find doing a presentation with something visual really helps in helping me remember what I'm supposed to say, and also it maybe helps the audience a little bit in understanding what I'm trying to communicate. So the model here is an actual ladder, and I've got things attached to it, and we're going to talk about those things, and I'll share with you my understanding about how we know how far away the stars are. The distance ladder is actually a series of different techniques that are different from one another in that they are good for certain distances, and they overlap a little bit. So it's that overlap that we have that creates a way to calibrate to make sure that the next one is still accurate, or as accurate as it could be. And we start off with trigonometric parallax. That is the most reliable, the most accurate way of measuring stars. And then after that, we have spectroscopic parallax, and we use Cepheid variables. And then finally, we use supernova. And those are the different steps that we have. And that's what I'm going to do here with the ladder to illustrate those different steps. The Greeks, the ancient Greeks, certainly had this idea. Possibly before them, the Sumerians, maybe the Babylonians, they had the idea that a circle could be divided up into different parts. And they see the circle being 360 parts because I think that they saw that the sun apparently went around the earth, back then that's what they thought, that the sun apparently went around the earth in about 360 days. And that was about the length of their year. So they took the circle and divided the circle up into 360 degrees. And as you probably know, each degree is divided up into minutes, and each 1 degree has 60 minutes. And then each minute is divided up into arc seconds. So you have degrees, arc minutes, and arc seconds on this thing. Now, I want to thank Will for handing out the pennies, because I'd like for you to take a look at the penny for a minute, if you would please. Take a look at your penny. And Will, if you'd get the lights, because people are going to need to, oh, you didn't get a penny?
I didn't get it.
Oh, man. I don't have any extras. Here comes Will. Okay, here he comes. Here he comes. Okay. Okay, thank you, Barbara. Thank you. Okay. Thank you. Here you go. This young lady here.
This is mine.
Okay. Now don't look. Do you know whose picture is on the penny?
Yeah.
You do. Okay, good. His name is Abraham Lincoln. You know how many pictures of Abraham Lincoln are on the penny?
Just two. There are two.
Two, that's right. That's right. Turn it over to the back side. If your penny is not really a worn penny, you might notice that in the Lincoln Memorial, right there in between the two middle columns, you can see the statue of Lincoln sitting there in the chair in the Lincoln Memorial. So there's actually two different pictures of Lincoln there on the penny, one on the front, one on the back. Take a look at the distance. Take a look at the distance between those two columns right there in the middle, okay? Take a look at that. And then if you would, holding it so you're looking at the back of the penny, hold it out, stretch out your arm like that and look at the back of the penny and look at the distance between those two middle columns. What we're looking at there is about 300 arc seconds. That's what we have, 5 arc minutes, okay, because there's 60 seconds in a minute, okay? So that's about 300 arc seconds there between those two columns if you hold it at arm's length. When we're looking at Saturn, we could fit 9 Saturns in that space. 9 Saturns would fit in that space between those two columns. That's how small of a space we're looking at when we look at the stars and we look at the planets. We're looking at really a small little tiny space. So we've got 300 arc seconds between those two columns. And Saturn, if you're looking at the rings, 9 of those Saturns side by side would fit into that space there. So we're really looking at a small space there. The ancient people, they knew about this thing, how to divide up apparent angular distance and apparent angular size. And they knew about something called parallax. They knew about parallax. Now, you too can know parallax. Again, without the penny this time. If you take your hand, your thumb, and stretch your arm out and close one eye and put your thumb on something that's on the other side of the room, okay? And then don't move your head and don't move your hand, but close that eye and open the other eye. You notice that it looks like your thumb shifts from one side to the other. That's because of parallax. That's because our eyes are in two different places. And that gives us a three-dimensional view of the world. Well, ancients knew that if the Earth went around the sun, in January we'd be on one side of the sun, and then 6 months later we'd be on the opposite side of the sun. Any nearby stars, any foreground stars, would apparently shift back and forth compared to the background. They knew about this, and this is stellar parallax. They tried to find it. All the way back to Hipparchus, Aristotle, they looked for this. They looked for stellar parallax, and they could not find stellar parallax because the stars are so far away. Even the closest star is so far away. So with the understanding of parallax and the understanding of the protractor, this man, here we go, this is going to be fun. This man, Frederick Bessel, was a German mathematician, and he was a very interested astronomer too. Frederick Bessel spent lots of hours measuring and noting the exact position of stars in the sky in the early 1800s. He spent a lot of time doing that. And he decided intentionally to find stellar parallax. He decided to do that intentionally. Now, by then they had invented telescopes, of course, 1600s, and he had a pretty good telescope. And so with his telescope and going intentionally, he knew where the stars were supposed to be. Understanding parallax and knowing how the degrees worked, he set out to find it in the 1830s. And by 1838, Frederick Bessel, actually discovered a nearby star, 61 Cygni, that had a stellar parallax, if I remember correctly, 0.1 arc seconds. Now remember the back of your penny. The distance between those two columns is 300 arc seconds, and here this is 0.1. So we're talking about really, really, really tiny little space, really tiny little distance. And it's actually a double star, And you can see here in this picture, this modern picture, Bessel did not take this picture, but in this modern picture you can see the little bump on the left-hand side that shows the second star there. Very small parallax, but he was successful. He was successful at discovering parallax of a star. And this was the first one. I've seen astronomy textbooks at the end of the 1800s, and by the end of the 1800s, many astronomy textbooks list about 20 variable stars that had been, not variable, but nearby stars that the parallax had been measured. So it was a real long process, an arduous process, trying to discover these stars that are close enough that we would be able to tell their shift back and forth as the Earth went around the sun. So the way we did this, the way they did this, finding in January the Earth would be on one side, and 6 months later the Earth would be on the other side of its orbit of the sun, and you'd see this shift like you did with your thumb. You'd see this shift back and forth of the star, and they could figure out the angles and one distance. The distance between the sun and the Earth would be 1 astronomical unit. And then the angles, they could figure out the angles, because if they did the full 6 months, that'd give them too long of a baseline, so they'd use just 1/2 of it. And so the angle between the Earth and the sun and the foreground star would be 90 degrees. And then the angle between the sun, the Earth, and the foreground star, they'd be able to measure that. Just by looking, they'd be able to measure that. And they had the space in between as 1 astronomical unit. They had angle, side angle. Now you kids out there, any young people who are taking trig, you probably recognize angle, side angle. Do you recognize angle, side angle? If you know angle, side angle, you can figure out all the other angles on the other side. So by knowing these 2 angles and knowing the one side, they were able to figure out the distance to 61 Cygni. And then when they found parallax for the other stars, they were able to figure out the distances to those stars. So parallax was a really good thing, but it was really hard to do because it's so small. The angle is so small, it's hard to see, and the stars are just so far away. So parallax. Another thing that really got involved here is another law called the inverse square law. The inverse square law works for gravity and it works for light. And so by using the inverse square law, we were able to understand something about the stars. The inverse square law is that if you shine a light and then you change the distance, you double the distance, you actually change the light by a factor of 4. I'm going to get off of this for a second. For example, my flashlight here, I've got a piece of paper on the wall, and if I stand a certain distance away, you can see the circle that's here. If I stand a certain distance away, I can fill that circle up with the center part of the light, if I hold it right. But if I take the distance, let's see, what is that, about 2 feet, 2 yards? If I double my distance, the light gets spread out over an area that's 4 times as much. And that's the inverse square law. Inverse square, you double the distance, so you've got 2 as the double. You put the 2 in the denominator and square it, so you've got 1 over 4. So you get 1/4 as much light hitting that space. With that information, with that understanding, and the understanding that we knew the distance to this star, we were able to figure out something about the star. And this was really exciting for astronomers because if the stars are all at unknown different distances, we really can't compare the stars. It's like apples and oranges and grapes and other things all mixed in, so we just don't know. But now that we know the inverse square law and we know the actual distance, we can do this little math, and please, I'm not going to make you do the math, okay? I'm not going to do that. But if the small m is the apparent magnitude, what we see in the sky, and the d over on the right, that's the distance. If we know those 2 variables, we can do this math in what's called the distance modulus, And we can figure out what the capital M is, and that's absolute magnitude. Absolute magnitude is how much brightness that star would be giving off if we were a given distance away. Astronomers have chosen 10 parsecs to be that given distance. So we could take every star there is that we can tell the distance and do this math and tell how bright it would be at 10 parsecs. We're removing distance from the equation. Now we can compare star to star to star and not have distance mixing it up. So we can actually do some comparisons of the stars. So absolute magnitude is able to be calculated, and we can compare the stars. Parallax. Problem with parallax, up on the ladder. One of the problems with trigonometric parallax is it only works for the closest stars. Only the closest stars. As I said, by the late 1800s, they had maybe 20. From the surface of the Earth, it's possible to calculate, to detect the parallax to stars of maybe 1,000 stars. The European Space Agency has a space telescope in orbit around the sun, called Gaia. And Gaia they just recently announced, you may have seen it in Sky and Telescope magazine a month ago, Gaia has determined not only the position, but the distance to about 1 billion stars. To about 1 billion stars. Now that sounds like a big number, and it is a big number. But if you compare that to how many stars there are in the Milky Way galaxy, 1 billion is small. That's our neighborhood. 1 billion stars is just our neighborhood in the galaxy. We just barely know the distance to the stars in our neighborhood. So even with the European Space Agency's Space Telescope Gaia, we still have an understanding of just the neighborhood stars. Now, this is the most accurate, the most reliable method because it's trigonometry, and we can tell for sure what the distances are. So I'm going to put this back here. There you go. Trigonometry. Questions so far? Okay, please. Yes, sir.
What's a
Parsec.
parsec?
A parsec is a distance at which you'd have an angle at one astronomical unit orbit of the sun of, I think, 0.1 of an arc second. It's like, help me out, 32 light years? Is that a parsec? I think it's about 32 light years. 32? 3.2. 3.2. And 32 is like 10 parsecs, and that's absolute magnitude. Thank you. So it's 3.2 light years.
How long does it take to travel a light year? How much
It would.
farther does that travel?
It would. I don't know how far light travels in a year. 6 trillion miles. There you go. 6 trillion miles. There's a lot of stuff I don't know. So thank you for asking. I just don't know that one. But here with trigonometric parallax, we can tell the distance just to a very few stars, a very few. So we've got this one out of the way, the most reliable, the one using math, the one using the protractor. Now built on that is spectroscopic parallax. And spectroscopic parallax is built on the spectrum. Now I've got this nice little flag here that's got not 7 colors like Sir Isaac Newton had, but 6 colors. I think Newton had to put in the 7th color. I don't remember, did he put in indigo? I think it was indigo maybe he put in, because he thought 7 was an important number. He didn't really like 6. But spectroscopic parallax is built on the spectrum of the stars. So that's our next step, spectroscopic parallax. About 100 years ago at Harvard, there was a program going on where they were analyzing the spectrum of stars. They were taking the light from stars, running it through a prism or a diffraction grating, and coming up with the rainbow. And they noticed in these spectra that there were black lines, absorption lines in these rainbow. And they noticed that they weren't all the same. They were different. Different stars had different black lines, different places. So Pickering, who was the director of the observatory at the time, he hired a bunch of women from the neighborhood. They were cheap labor. They were called computers. He hired these ladies to come in and look at the spectrum and put them into categories. Put like with like and different in a different pile. And so these computers, these ladies were working there. Annie Jump Cannon was one of these ladies who was working there. And Pickering, the director of the observatory, just arbitrarily assigned letters of the alphabet to the different piles of spectra. Pile A, pile B, pile C, and so on. And the ladies were just putting the spectrum in these piles, depending on putting them like with like. Annie Jump Cannon was looking at these spectra, and she decided that there was a better way. There was a different way. Now, a word about women in astronomy. Astronomy has done a poor job of being inviting to women. Women have done some of the most amazing discoveries and some of the most amazing work in astronomy, and we have done a very poor job. 100 years ago, many observatories would not even let women in to the observatory. They weren't allowed to look through the telescopes because, oh, it was science, it would hurt their pretty heads. Okay, some stuff like that. We've done a really poor job. I challenge you to be more inviting. It's hard work, but women can really add some important stuff. They have in the history of astronomy, despite being repressed. They have done some great things in astronomy. Annie Jump Cannon is one of them. Here's one of these lowly computers at Harvard. She looked at more than a quarter million spectra. Can you imagine that? 250,000 over her time there. And she decided that there was a better way to organize it than A, B, C, D. She noticed that the black lines, these absorption lines in the spectra, made more sense if you organized the letters in a different way. That you'd have the black lines appear and get thicker and then disappear in different places if you did this, if you put them in this order. And you can see here the black lines as they would appear and disappear in different places in the spectrum. And she reordered it, so instead of A, B, C, D, it's O, be a fine girl, kiss me. Well, that's the mnemonic, how we do. O, B, A, F, G, K, M. This was groundbreaking. This was an amazing thing that she did. This laid the foundation for some real understanding of stars. Now, there's a little bit of trouble to it because you're getting a little bit further from the ground, and it's a little bit risky up here, okay? You're getting a little bit risky, but if you can look at the star and tell its spectrum, we found out that that tells us its temperature. And these two scientists, one in Europe and one in America, at the same time, made a graph. This is called the Hertzsprung-Russell diagram, named after two scientists, Hertzsprung in Europe and Russell here in America. And across the top, you can see O, be a fine girl, kiss me. And that's temperature. The hot stars are over here. These are really hot stars. And then cool stars over here on the right-hand side. And our star is a G3. We're right about here. Okay, our star is a yellow star right about there. And Hertzsprung and Russell developed this diagram, and they could tell the absolute magnitude of nearby stars because of the protractor, because of trigonometric parallax. They could tell that. And they noticed in plotting the stars, there were basically different families. That we had the main sequence, which is a diagonal line that runs left to right here. 90% of the stars end up being on the main sequence. 90%. We have a couple stars up here, some stars up here, so a few stars up here, and a lot of stars down here. Let me ask you. Here we have some stars. Here's the temperature up here. And we have some stars here like our sun that's this bright, but it's this temperature. How can a star be the same temperature but be brighter? How can a star be the same temperature but give off more light?
How about bigger?
Bigger, there you go, bigger. Now we're not talking about how it appears to give off more light, but to actually give off more light, okay? And these stars are bigger. So the way this star can be the same temperature but give off more light, be more luminous, is be bigger. So we have giants, we have supergiants, and then we have these stars down here. And these stars, some of these stars are very hot. How can a star be very hot but give off less light?
The opposite?
Be smaller, that's right, to be smaller. And so these are white dwarfs. But most of the stars that they looked at fit right along here on the main sequence. 90% of the stars in the sky ended up being a main sequence star, like our sun. This is where stars are happily fusing hydrogen and helium in the core, and this is where they spend most of their lifetime right here, okay, on the main sequence. Now, here's the trick. For these stars that are close enough that we could tell the absolute magnitude because we knew the parallax, that works. But how about stars that are further away? Stars that are maybe not in our neighborhood, but on the other side of the Milky Way galaxy. We could assume, that's a big word, we could assume that the star is going to be main sequence. Is there a chance we could be wrong? Yes, there's a chance we could be wrong. But we can assume 90% of the time, that's pretty good odds. It's going to be main sequence. Now notice the main sequence here, this swath of main sequence, it's not a line. There's some width to it. There's places where it's wider. So we'd have to assume if we can find a star and we can tell its spectrum, its spectral type, by looking at the spectrum, and we come down here, does it go here at the top of the main sequence or at the bottom of the main sequence? We have to make an assumption. But once we make that assumption, we can read over here and find its absolute magnitude by using the HR diagram. We can take our eyeballs and look up at it and figure out its apparent magnitude by looking at it, and then, more math, use the distance modulus. This is the same equation as before, but this time, we can see the apparent magnitude. We can use the HR diagram to get the absolute magnitude, which is the capital M, and by doing the math, we can figure out the distance. We can figure out the distance to stars by using the spectrum and on the HR diagram. Now this works for a lot more stars. It works all the way out to the edge of our Milky Way galaxy. So we get a lot more stars. We understand a lot more stars and how far away they are, and we can understand how big our Milky Way galaxy is. But that's all. Here we are on the top of that step, okay? It's going to be fun, isn't it? This will be fun, okay. So there's spectroscopic parallax. So we've got the most reliable, which is trigonometric parallax. We've got the second most reliable, which is spectroscopic parallax. It's a little bit unsure, okay? You're up a little bit higher, okay? Up a little bit higher, but it's based on that. And we can tell by the overlap, we can tell that at least the stars that are overlapped, they work both ways. Both ways measure them correctly. So we can assume that spectroscopic parallax does a pretty good job with that. Women. Henrietta Leavitt. She was another one of those people who worked at Harvard Observatory 100 years ago. She was a paid astronomer there. She was given the job of looking at the spectrum of some stars around the celestial North Pole. And she did an amazing discovery. I think it was 1912 she made this discovery. She was looking at a variable star. Whoops, variable star. Got to get my props going. She was looking at a variable star in the constellation Cepheus. And variable stars are stars like our sun, but they actually change in brightness over time. Now there's different kinds of variable stars. There's eclipsing variable stars, which really don't vary in themselves. They just, maybe there's two stars and one passes in front of the other and it looks like they change brightness. But then we actually have some stars that change brightness on their own. And Henrietta Leavitt discovered that this particular star in the constellation Cepheus had a light curve. This is a light curve, and here shows the brightness here over time, and has a light curve that goes up and down, up and down, up and down in a regular sort of way. In a regular sort of way. And here's a more modern version, okay? That other one was from Henrietta. But here's a Cepheid variables light curve. And you can see in the light curve that the distance between the bottom and the next bottom, or the top and the next top, is about 10 days. So it takes about 10 days for this star to go from bright to dim and then bright again, about 10 days. And Henrietta Leavitt noticed that this star had a pattern to it, because she was able to use spectroscopic parallax on some of the nearby stars, and she could tell, oh, wait, what happened? Oh no. Did I go forward? Oh no. Could you help? If you could take me back to Henrietta Leavitt, that'd be great. Thank you, I appreciate it. There we are. That's great, thank you. I'm sorry. I hit my button. There she is, appreciate that, thank you. She discovered that if you carefully measure the period, how long it takes to go from bright to dim to bright again, if you carefully measure the period of these variable stars, now you can't do other variable stars, if you could do these variable stars, you would notice a relationship between the period and the absolute magnitude of the star. Now she confirmed this by using spectroscopic parallax. But here, stepping beyond the Milky Way, looking at stars that we could not look for their spectroscopic parallax, we had to use something else, we were able to determine their absolute magnitude. And if you can determine their absolute magnitude by using this period luminosity law, and then you could look at the star with your eyeballs, you'd have the apparent magnitude and the absolute magnitude, and then this wonderful math again. And we'd be able to figure out, because we have the apparent magnitude and the absolute magnitude, we'd be able to figure out the distance of these stars. Henrietta Leavitt did that. It's because of Henrietta Leavitt's period luminosity law that we're able to look at the distances of these stars that are beyond the Milky Way. Now, a guy named Edwin Hubble, you probably recognize his name, Edwin Hubble used these Cepheid variables, looking at some of the smudges that were in his telescope, and he recognized that some of these smudges had Cepheid variables that had this light curve, and he calculated the distance using this math, and he found out that some of these smudges are way outside the Milky Way, that these are other galaxies. Edwin Hubble used this to discover other galaxies. He discovered that the Andromeda galaxy was 3 million light years away, and he discovered that there were other galaxies out there that are even further away. But it's because of Henrietta Leavitt and the period luminosity law that he was able to do that. How's that blue light? Is that bothering you? Is that okay? I'll leave it on then, just for fun. So, so with the period luminosity law, we're able to find the distance to stars outside of our Milky Way galaxy and all the way around the Virgo supercluster. The Milky Way galaxy belongs to a group called the local cluster, the local group right here. Here's the local group. And the Milky Way is one of those little smudges there. And then the local group is part of this cluster of clusters called the Virgo supercluster. And with Cepheid variables, we can go out to 100 million light years. 100 million light years. And we can find the distances. Now this is a little bit tricky here. The delta Cepheids, there appear to be two different kinds of delta Cepheids. So you got to know which one you're looking at, okay? And you've got to time it correctly, and you got to measure it correctly, and then you've got to figure out the absolute magnitude correctly. There's all sorts of assumptions here. It's a little bit trickier. It's a little bit trickier here, but you get up a little bit higher, and you're a little bit more unsteady. Our calculations are a little bit off, a little bit more, but it's based on trigonometric parallax and on spectroscopic parallax. And then finally, this is too high. Okay, there, I feel better now. And then finally, on Cepheid variables, and that's what Edwin Hubble used. So this is the cosmic distance ladder, but we're not done yet. This only goes out to the local, to our Virgo supercluster. We have to use supernova to get this next step out, supernova. Now, supernova, as you probably know, is a star that blows up. And there's lots of different kinds of supernova. That's one of the problems of this last step. There's a lot of different kinds, and you got to know which kind you're looking at to be able to use it correctly. Going back to the HR diagram, if you notice the white dwarfs down here, the white dwarfs can be almost any size under about 1.4 solar masses. They can be smaller than that. They can be up to that size. They can't really be much larger than that, 1.4 solar masses. This gentleman, come on. No, what we have here is, in this picture, is an artist's rendering of one certain kind of white dwarf. Most stars seem to be parts of families, that there might be 2 or more stars all come from the same gas cloud. And in this case, we have 2 stars, a binary system, and generally, you're not going to have 2 stars that have the exact same mass. So they're going to evolve differently. That one star is going to reach the end of its life, the white dwarf stage, faster than the other one will. So here we have the white dwarf here, and then the companion star here, which is still in maybe its giant phase. And they're close enough so that the gravity from the white dwarf is pulling matter off of the companion star, and this matter is falling onto the white dwarf. Now, if a little bit falls onto the white dwarf, then it might have some small eruptions on the surface. But if a lot of matter falls on the white dwarf, something remarkable happens. And it's because of this guy right here, Chandrasekhar. Chandrasekhar was an Indian well, he was Indian. He moved to England and did his education in England. And then he came to the United States. I think it was at Yerkes. He was at Yerkes, I think. And he realized what would happen if a white dwarf had too much mass. If a white dwarf gained more than 1.44 solar masses, the pressure of that mass on the star would be beyond what the star is capable of, and the star would explode and blow itself into pieces. A supernova explosion. This particular kind of supernova would be a type 1A supernova. Very little hydrogen, because the white dwarf has already burned off most of its hydrogen. So Chandrasekhar came up with this idea that 1.44 solar masses is sort of the limit for white dwarfs, and if you get more mass on the white dwarf, it blows up. You know what I'm going to do with this, don't you? Okay, yeah. Now, what happens is that the white dwarf, when it blows up, almost all the white dwarfs that are in this type 1A supernova are about 1.44, 1.45 solar masses, because at that point, boom, they blow up. So they have about the same mass, which means when they blow up, they have about the same absolute magnitude. Their absolute magnitude is something like -19. No matter where they are in the universe, when you have a supernova type 1A, it's a -19. And if we know the absolute magnitude, and we can look at it and see the apparent magnitude, we get the light curve from it, we use this math again, this distance modulus math. We know the apparent magnitude because we look, the absolute magnitude because it's a type 1A, so we know it's about -19. We can figure out the distance by using that math. So let's see, I've shown you the protractor, I've waved the flag, I've turned on my variable star. I think it's time to blow something up to represent a supernova, okay? So, let's keep those off, okay? Let's see if there's any flash on this. I checked about the insurance here. I don't think they have any. So this ought to be fun, okay? No hydrogen. Yeah, I know about the Hindenburg. I'm not going to do that. No, and type 1A supernovas didn't have very much hydrogen in them, because by the time they'd become white dwarf, they had already fused most of their hydrogen into helium or other things. So you're not going to get any hydrogen, so no hydrogen here. Okay, good. Okay, you ready? Anybody taking a movie? This is the time to do it. Okay. Let's see if it works. Let's see. Oh, no, don't go out. There you go. Pow. So there we have a supernova explosion. Okay. No, it's just a balloon. But remember, all models are wrong. It's just some are useful. So there we have supernova. We can reach out further into the universe. And by using our understanding of how these type 1A supernovas work, and by understanding the math of that distance modulus of knowing the apparent magnitude and the absolute magnitude, we can figure out by using the math the distance to galaxies that are far, far away. So there's the end of our cosmic distance ladder. So we've gone from trigonometric parallax to spectroscopic parallax to Cepheid variables and then to supernova explosions. So I want to thank you very much for your kind attention this evening. I really appreciate that. And I'd like to open it up to any other questions, maybe some questions I can answer, but I don't mind questions that I don't know the answer to, okay? They always make me think when you ask questions that I don't know the answer to. So thank you very much. Questions? Yes, sir.
How far away are the stars? You already tell us.
61 Cygni. 61 Cygni, which is the one that Bessel discovered. He was using telescopes that aren't as powerful as ours today. He was within 6% of his calculation about how far away the star was. It's 10.3 light years. 10.3 light years. Now, of course, we have stars that are closer. Proxima Centauri is much closer, and they've just discovered an Earth-sized planet in orbit around Proxima Centauri, which is very exciting. And I think it's something like 3 light years away. Is that Proxima Centauri? Proxima Centauri, 3 or 4? 4. So it's within almost distance. Within almost distance. I guess a trip to Proxima Centauri might take us maybe 4 generations, 5 generations, 15 generations. So it would take us a couple generations to get there, okay? But that's close. So we have the 61 Cygni 10 light years away. We have the Milky Way galaxy itself is about 110,000 light years across. So the other side is that far. And then we have the Andromeda galaxy, which is about 3 million light years away. And then we have the observable universe, which is what? We think we're 14 billion years old, something like that. 13.78. So we have that. So that's how far away the stars are. Okay, thank you. Thank you for asking. I never did say that, did I?
Being facetious, but then I also wanted you to do just what you did.
Okay, good.
job.
Thank you. Thank you for asking that. Well,
Take a stupid question.
no,
and you answer.
not a stupid question. No, I've been teaching for more than almost 40 years, so a good question. That was a good question.
Should be catching on.
Okay, other questions? one of these days I will. You had a question, didn't you? Did you have a question? Okay. Any other questions? Please. This is what I live for, questions. We're not going to let you out unless you ask a question. Okay. Well, Brandon, I guess that's it. I thank you very much. Thank you very much, ladies and gentlemen, for your time and your attention. Appreciate that. It's all yours.